So we have Emma Brouwer visiting NIH for 2 days now. Emma is a physicist at the Spinoza Center, working with Wietke van der Zwag and Serge Dumoulin and Nikos Beoulous. In my circles, she's mostly famous for her high-resolution MRI and fMRI work, specifically in the cerebellum, looking at kind of motor function and digit representations across the tiny lobules. But you're doing all kind of other stuff as well, like with MS and PTX and those kind of things. Feel invited later. After this presentation, we have a group lunch in the SFIM conference room, but also later today, we are gonna go for an informal dinner at Rock Bottom. Everybody's welcome. I think maybe we will gather there at 5:30 or so. And this is being recorded, and Emma's title is Cerebellar Imaging Using 70 MRI.
Thank you. And thank you for inviting me here. I'm really excited to be here in real life. And yeah, I will be talking about cerebellar imaging using 70 MRI. But before I start, I will introduce myself. I'm hearing echo. That's me, sorry. Oh, okay. I'll introduce myself a bit more. Let's see. Works. Yes. So I grew up in Brussels, the city of fries and chocolate. And then I moved to London, and this is where I studied. So I did a bachelor in physics and philosophy, and then I did a master in physics. And after that, I decided to go into the field of MRI. So I moved to Amsterdam to start my PhD at the Spinoza Center for Neuroimaging. And yeah, here is the group of the Spinoza Center. And during this presentation, I'll cover most of the projects that I've done during my PhD. So I'm finishing it up in a few months. I was also doing a project a year ago in Zurich at the 70 scanner there. And I was doing this with Karin and Marcus Nielsen. So I will be talking about all of these projects. And what they all have in common is the cerebellum. And as you might know, the cerebellum is very different from the rest of the cortex. So if we find over 15 billion neurons in the higher part of the brain, in the cerebellum, we find over 70 billion neurons. So it's much denser in the amount of neurons. And you can already see that from its anatomy. So here is a zoomed in image. And anatomically, you can also see that it requires a higher resolution to actually see its foliations and its structures, because it's very different compared to the foliations you're seeing in cortex. And therefore, the 70 scanner has been a big part, actually the only part of my PhD. So we always have done the project on 70 or higher, imaging the cerebellum and trying to capture its structure and function in vivo. So here is another image of the cerebellum where you can see its foliation in even more detail. But very generally in the literature and in neuroscientific studies, it's referred to with different lobules. So here you can see different cerebellar lobules highlighted by different colors. And because it can be difficult to look at these lobules and the structure in 3D, sometimes they're also mapped on a more surface area, which you can see here. So these are the same lobules, but then presented on a flat map. And it's quite common to use these kind of maps as well in cerebellar imaging to sort of distinguish the different areas and get a better feel of where certain functions are happening. It used to be the case that basically motor function was associated with the anterior lobe, so that's the top lobules of the cerebellum, and cognitive function was more associated with the bottom lobules of the cerebellum. But this is a very broad sort of assessment of cerebellar function. And in the last decade, especially with the rise of high-resolution MRI imaging, we've gotten a much better feel of where these functions are. And here's an example of a study by Atlas by King et al. And you can see that functions, they're both cognitive, motor functions, but very specific functions as well. Eye movements, hand movements, word comprehension, they've been related to different parts of the cerebellum. And what we also see, if you compare this image, where you can see the lobules, to this image, that these functions are really not following these lobular boundaries. Like they are, yes, there are some lobules that are more associated, for instance, lobule 5 and 8 are more associated with motor functions. But overall, these functions do not adhere to these lobular boundaries, which means that we usually think further than just the cerebellar lobules into smaller details to properly try and map its function. So before I start, I want to give a bit of a disclaimer, and that is that this is the layer fMRI group, of course, but it's very hard for me to talk about layers in cerebellum because cerebellar layers are very different, and there are less cerebellar layers compared to the layers we find in the gray matter of the cortex. And here is an example of that. So here's the white matter, and the gray matter consists of these three layers. So we have the granular layer, which is a layer with granule cells. Then there's a very, very thin Purkinje cell layer, and then there's the molecular layer. So there are sort of three layers, of which the middle one is very, very thin. And yeah, I will talk about layers, but sort of in its own cerebellar way, because at this moment we're not able to map fMRI responses through these layers, at least not yet. So what will I talk about? Well, a lot of different cerebellar topics. Cerebellar arc shimming, cerebellar macrostructure, somatotropy, proprioception, multiple sclerosis, and microstructure. Now, these titles might not look very coherent to you at this moment. I hope they do at the end of the talk. But overall, it means the first two, how can we visualize the cerebellum at 7T? How can we properly see it? And how can we see its structure? Then there are three topics on how does the cerebellum work? How does it work functionally, but also in disease, in multiple sclerosis in this case. And then the last one is sort of a hint towards, can we actually see cerebellar layers and how can we do such a thing? So I will end with that. Yeah. But let me know if you have any questions also throughout the presentation. Yeah, so to start with our shimming, I start with this because we need it for all the other projects. The cerebellum has a location which is not great for the RF wavelength that we find at 7T. So even though we need the 7T scanner to properly capture its structure, we need the SNR, the wavelength becomes shorter. And since the wavelength is about 10 centimeters at this point, it tends to destruct exactly in the cerebellar area. So here is an example of a flip angle map of the whole brain. And here, approximately here, is the cerebellum. And as you can see, we really have a lower nominal flip angle percentage, and that is because these waves destruct exactly sort of in the cerebellar area. And this causes an inhomogeneous signal and also a lower signal in the cerebellum. But luckily there is a solution for this, which is arc shimming. So for these studies, we're using the Nova Medical so the PTX coil with 8 transmitters. And what we can do is we can highlight a cerebellar ROI for a specific participant, as is highlighted on the left of the slide. And then we can calculate what offsets to give these transmitters in order to shift the interference away from the cerebellum. So to construct the field in the cerebellum and destruct it somewhere else in the brain. So if we had the flip angle map here, then you can see once you have quite a dark, you see like the cerebellum is very dark here, and if you use the personalized shim, you gain this and you lose signal at the front of the brain. So we're not shimming the entire brain, we're just shifting the problem somewhere else to where we don't want to look at this moment, basically. The only problem with this, it works well, but the problem is that it takes time because you need to make an ROI for a specific participant. You need to acquire this scan, you need to calculate the offsets. And if you're doing that during a scan session, which is possible, it takes about 7 minutes or so, which could be a whole fMRI run. So we don't want to put our time into this during our scan sessions. So what we did is we used a min-max approach to optimize this across participants. So we tried to see if we use different participants as a training group, if we could make a shim that is working for all participants. And that looks somewhat like this. So we get very similar results, a very similar shift of the flip angle maps, and a better signal in the cerebellum. So how does that look in practice? Here is an MRI image that we wanted to show for illustration. And you can see that in the unshimmed area, you get this loss of contrast. So especially in the posterior lobe of the cerebellum, you lose contrast. Whereas if we use the personalized and the universal cerebellar shim, we gain this contrast in these areas. And you can see the destructive interference here leading to loss of signal in the frontal areas of the brain. And the biggest difference between the two right images is that for one, you need over 7 minutes, and the other one is a matter of copy pasting a file. So you're gaining this time during your scan sessions. So once we have shimmed the cerebellum, we can start looking at it and image it. And we can start looking at cerebellar structure. And a lot of the software pipelines looking at brain images, they use surfaces, of course, to represent functional activation, and gray and white matter segmentations are also needed for this. But the cerebellum just doesn't fall into these automated pipelines because it just has a very different structure and it needs its own pipeline and its own way. And here again, that's highlighted by the difference of cortical foliation on the left and about 15 times smaller foliations on the right side in the cerebellum. So we're really looking at orders of magnitude smaller foliations, and therefore looking at the structure and looking at surface areas can be quite difficult if you use the standard pipelines. Here's an example of that. So this is the white matter segmentation of the brain, of the cerebellum, and at the bottom you can see what you commonly get if you use a standard pipeline for cortical segmentation. So you get the white matter here, but the branches are really lacking in the cerebellum. And if you use a more optimized pipeline and a 0.6 millimeter isotropic image, you really do start to get branches of the cerebellum, and you can see individual lobules. And yeah, we're really starting to see the white matter of the cerebellum and its foliations using this kind of structure. And then what can we do? We can take this part, so the cerebellar white matter, and we can map it in the 3D space. So we can basically look at a cerebellar surface, just like this is commonly done in the cortex. We can also inflate this surface and look more at the gray white matter foliations, and then you get a cerebellar surface in 3D space, and this really allows also to have an extra way of looking at it. So next to the flat maps, you can also look at it in 3D space, and thereby you get an extra degree of freedom to see shifts in functional activation. So this is something that we use also for our fMRI studies. And one of those studies is in cerebellar somatotropy. So of course, in the cortex, we know that neighboring areas are very often located, so hands or feet or somatotopic maps can be made in the cortex. The cerebellum also has such larger somatotopic maps, but just as studies in the cortex shown looking at different actin maps of motor tasks, we actually wanted to know whether such tasks, such as here, flexing and extending of the hand, would be different in the cerebellum too, and if we find different activation patterns on a smaller scale in the cerebellum. So that was the goal of this project. In order to explore this, we used 3 different tasks. So we scanned 9 volunteers, and we did 3 different tasks during a block design. So there's a flexing task of a participant flexing into a ball, and they basically flexed a different digits randomly into the ball for 12 seconds. And the same was done for extending. So then it's into an elastic to get the same digit moving, but in a different way. And then we had a stroking task of which the participant's hand was stroked with a toothbrush in the scanner for also the same different digits. And the setup looked like this. So we have the 0.6 millimeter beta rate I showed earlier for the segmentations. And then the black box indicates the EPI field of view. And here you can see the EPIs in 3 different orientations. So these were the images we were working with during the study. First, we looked at this in the 3D space. So what did our activation map show? What could we get out of this? And very exploratory, what were the differences? So a main difference was that in the extending task, we get this bilateral cluster. So here you can see clusters for each digit. So 1, 3, and 5, all in the left hemisphere, even though the task was performed with the right hand. And we did not see this. So the right is here, and the left is here, and the task was performed with the right hand. And we didn't see that for the flexing and stroking tasks. Sometimes we saw a small cluster, but with extending, this was really a constant finding. In the cortex, studies have shown that more difficult tasks could potentially also cause activation to happen in the opposite hemisphere. So it could be a similar method, but yeah, we don't necessarily know why this is happening. When we look at cluster size, we also saw a difference, namely that the two motor tasks had a larger cluster in the anterior lobe compared to the posterior lobe, whereas the stroking task had very similar size clusters in the two hemispheres. So posterior is the top, which is here indicated with P, and anterior is the that's the top of the image, and posterior is the bottom of the image. And technically, in a lot of cerebellar studies, you can see that there's differences between the anterior and posterior lobe, and there's a clear distinction between its function. So that's also why we compared this to see if we get such differences. But of course, we're still in sort of the 3D space, looking at the size of the clusters, but we want to now use the surface that we have in order to see if we can find any spatial differences between these tasks. So here's an example of the extending map. You can see in the anterior lobe, and here is the posterior lobe. Yeah, from this image, I think you might be able to see that in the posterior lobe, it's already more difficult to actually make a cerebellar surface. And we see here that we have these sort of bridges, and it's less defined compared to the left image. And this is due to the fact that the posterior lobe might require an even higher resolution in order to capture its foliations properly. The anterior lobe has a bit larger foliations compared to the posterior lobe. So even though we saw specific patches, so these are different digits, different colors, it was really hard to still see spatial shifts in the posterior lobe on the surface. But on the anterior lobe, here is the map across participants. So each row is a participant. You can basically see the different digit maps across participants and tasks. And two things became apparent looking at it in this framework, is that the blue cluster, which is the thumb, is relatively more medial and always found to the right of this image. For all tasks, we do see that for most participants. So here you can see blue, blue, blue there. But what was more convincing and what also became apparent is that if you zoom in across all participants, this gray cross is a sort of, it's the same across these images, so in the same location. We see that for flexing and extending, the task was found to the right of the cross. So here on these two sides of the cross, whereas in the stroking task, it was always shifted more to the left. So here you can see that to the left of the cross, you can see the task pattern for stroking, whereas for flexing and extending, this is more shifted to the right. So there seems to be this spatial shift mediolaterally for flexing and extending versus stroking. So these motor tasks, more motor heavy tasks, they overlap more than the sensory task. There was another study on cerebellar proprioception that we did. So proprioception is basically the idea of where your body is in space. So you use it in your everyday life all the time. For instance, when balancing on a leg or when drinking a cup of coffee, it's and we don't really know how it is presented in the cerebellum and how involved it is with the cerebellum. So we did a similar setup as we did for the proprioception, for the somatoscopy study, using the same EPI and anatomical images, but now a task of one block design, where on the left you can see midline contralateral finger tap, which is a task in which the participant was laying in the scanner bore. They couldn't see their hands because they were laying in the scanner and they had to match their fingers. So it's trying to match your arms in space without looking at them. So it's quite difficult to do from experience. And you basically try to match digits that are shown here on the screen quite quickly within a block. And then the idea is that we can contrast this with the SAF experiment, which is a simultaneous unilateral finger flex. So you have the same digits that are being moved, but now you're not trying to match them in space. So this contrast, the hypothesis is that this task engages more proprioceptive need compared to the simultaneous unilateral finger flex, and we wanted to know if there were differences between these two. So we can look at this as shown on the left within the 3D space. And I think if you look into the white circles, you can see that the orange, which is the less proprioceptive task, has a different location compared to the MCFT task. So you can see that, for instance, here it's more here, more anterior, and here you can see it shifted a bit upwards. And both of these activations are located in the cerebellar hand areas, which are lobules 5 and 8 are the main areas for cerebellar hand movement. But from the animal literature, there is a hypothesis that in animals, well, it's been shown in animals that proprioceptive behavior and responses are actually found deeper into the fissures of the cerebellum. So it's important to note that it's not about a layer, it's not deeper into a layer, because you can see here, this is the cerebellar folding, but it's deeper into the fissure. So if you were to plot this on the surface, then you would get a sort of patchy activation, because you would get here orange, and then you would get blue, and then you would get orange again. So using the surface here is not necessarily the best way to look at the activation if we're looking for this specific organization. So we decided to try something else. Namely, so we used Laney, but not to look at the cerebellar layers, but we looked at the depth into the cerebellar fissures. So here you can see the segmentations that we used as input. So you have the outside of the cerebellar lobule 5 and the outside of cerebellar lobule 8 depicted in white. And then we used the maximum amount of layers that we could generate from that. And here you can see a segmentation in the cerebellum based on these different segmentation steps. And then the hypothesis would be that if we have a similar organization, as you can see on the right, that we find in animals, then we would have to see that the more proprioceptive activation, that this contrast would increase when going deeper into the fissures. For completeness, we also did the segmentations in medial-lateral direction. This very commonly you also see medial-lateral organization in the cerebellum, and we did the posterior-anterior segmentation steps as well. So what did we find? In lobule 5, which is the upper lobule here, on both sides, we did not see this difference. So we did not see the contrast of the proprioceptive task. We saw no change over depth, whereas in the posterior lobe, we saw differences similar to what we saw in the animal literature. And in the medial-lateral direction, we saw that this in fact did change significantly across these layers in lobule 5, but it did not in lobule 8. So what we're seeing is a difference again between this anterior and posterior lobe, and this is very common in cerebellar imaging and function studies. Yes, so we again see that they do tend to be very different from each other, the anterior and posterior lobe, and it's important to also look at them separately, I believe. So now I will talk about multiple sclerosis in the cerebellum. Multiple sclerosis can affect the cerebellum by resulting in atrophy or cerebellar lesions, and these are quite common in the cerebellum. So what we wanted to do This study is still ongoing. So far, we have scanned 6 MS patients and 3 healthy controls, but we are scanning many more currently. And what we wanted to do is, it's more an exploratory study, so looking at how the cerebellum is different in MS patients compared to healthy controls. Also because generally studies tend to exclude the cerebellum, and there is very little known on the cerebellum in MS due to its structure and the imaging methods needed to see it. So we decided to do a 400 micron isotropic MP2 range image with perspective motion correction. Here is an example of that in a healthy control, and here is an example of that in an MS patient. So you can already see, I believe, the difference at first. So you see more atrophy in the MS patient's brain, and also 2 lesions are highlighted here. So 1 cerebellum and 1 in the cortex. The plan is also to look at these images and compare them to the 3T scanner results, because this is the scanner that's most used in clinic for MS patients currently. And so here's already an example of that. And the plan is to see if there are lesions that we can see on the 7T that we can't see on the 3T. And also if we can find anything else at this resolution that we didn't know we were looking for, of course. On top of that, we also, during this session, did a functional task. So we did a motor task of moving the right hand, and we looked at connectivity throughout the cerebellum from this motor seat area. And these preliminary results, so they're of very little participants, show already that there is a stronger motor response for healthy participants compared to MS patients, and we find the same for the connectivity results. But yeah, once we have scanned more participants, we would like to look into the details of this more. And then there is a final protocol in the study that we use, and that is a single slab, so a 2 by 2 by 0.5, so a 200 micron image of the cerebellum. And we use this to scan. Here you can see it in a moving frame. So we want to zoom into a specific part of the cerebellum and see if this 200 micron resolution can provide us with even more detail on top of the 400 microns. This is also, of course, performed with perspective motion correction. And this is also a zero contrast. So here you can see one of those results. This is in a healthy volunteer. But we also have done this in MS patients now. So we'll move. We're now at 200 microns in the cerebellum in vivo, but we want to also see, okay, what happens if we can go onto even higher resolutions, and we can do this, but we can do this in post-mortem imaging. So we have a project with Maastricht University where they used a 9.4 Tesla scanner to obtain full brain, whole brain resolution, 200 micron isotropic, but also of 100 micron isotropic images. And these images can be very useful to see what is possible if we had even more resolution and even better imaging methods to see the cerebellar structure. So of course, this study looks at the entire brain, but we specifically wanted to know if, well, first of all, if we could segment the 200 micron image white matter using these data, but also if it's still improved if you go to 100 microns isotropic, because where is this limit of just segmenting the white and the gray matter in the cerebellum? What resolution would you need for this? So this is an example of the 200 micron isotropic image. And then we segmented the white matter in these for both resolutions. So at the top, you can see the 100 micron image, and at the bottom, you can see the 200 micron image. Both of these segmentations, I believe, look, we're entangling a lot more white matter in a lot more detail. And here you can zoom into the red squares highlighted on the left. And we still see that the segmentation pipeline misses things in the 200 microns. So here, the left, you can see that the white matter branch is sort of interrupted in the 200 micron image. And overall, we looked at the whole volume of the cerebellum and comparing this in the 100 and 200 micron image, we do see that we're still underestimating the white matter surface, so the white matter segmentation, and thereby the surface of the gray matter. And this is very common in the cerebellum. And also, to put things back into perspective, if we start by our image that we had at the beginning of the talk, at 0.6 millimeters isotropic, we really are gaining resolution. And we see here that we're missing a lot of the white matter structures when looking at, when we're looking at in vivo MP2 ranges that we can use during fMRI studies. I believe the main thing is also when you're doing fMRI experiments and you want an anatomical image, it's really a balance between how much time do you have for the functional task and how much time do you have to optimize your anatomical image. And this 0.6 protocol has been sort of the result of weighing these two things. So you can do this, I believe, in about 10 minutes, which is relatively okay for the surface that you can get. But if you have more time, you can go in higher resolutions. So now I'll go back to the question of the layers. So I haven't really shown you the layers of the cerebellum, but I believe that maybe if we look at a different contrast, we can get more information, and I can maybe tell you something about the granular layer with the granular cells. So this is the project I did in Lund University a year ago, and it basically looks at if we have our anatomical image here at 400 microns, can we get information from a histological image, which you can see on the right, in vivo in MRI. So the image on the right shows the histological staining, where the blue here is the white matter. The sort of dark green area next to it is the granular layer, and the molecular layer is the outer layer. This granular layer is affected by many different diseases. Okay. Diseases such as Alzheimer's disease, multiple sclerosis, but also COVID-19. And we know this from postmortem studies. So patients who we can see the stainings after they have passed away. And then what they find is that the granular layer is often thinner as a result to certain diseases, or sometimes it's not thinner, but this depends. And basically its thickness has differences across disease perspectives. But also in healthy volunteers, studies show that the posterior lobe has a thicker granular layer compared to the anterior lobe. So it would be very useful to have this measurement in vivo, because then we could compare it while people are in the scanner. And so that was basically the main goal here. And to do so, we wanted to use the diffusion properties of this granular layer, because the granular layer has very densely packed layer. It has most of the neurons in the whole cerebellum. And these granular cells, they have a diffusion restricted in all directions. So instead of using linear tensor encoding, where we apply a gradient in a single direction and we can capture directionality, if this would work, in one direction, we could use spherical tensor encoding and thereby capture diffusion restricted in all directions, which is very specific to the cerebellar granular layer. And luckily, this was implemented at 3T. So here, this is the study, this study by Fils et al. And this is basically what caught my eye before going to Lund, and why I wanted to go to Lund, because you can see here that using this method, we get a contrast that really lights up the gray matter of the cerebellum. So you can see a much brighter contrast here compared to the rest of the brain. And I really wanted to implement this at the 70 scanner, mostly because I believe that if we have this measurement available at 70, we could combine it with other measurements at the same time. So anatomical images, functional images. So that was the goal of this study. Let's see. Because we had basically we wanted more SNR, what we did is we also used super resolution, and I also used that at the 3T. So here's the acquisition. It's a 1.77 millimeter isotropic voxels, and we rotated around the cerebellum. So all rotations contain the cerebellum, but we rotated around the center of the cerebellum to then use offline reconstruction in order to gain the resolution. So then we arrived at a resolution of 1.7 millimeters isotropic. And we used 2 different B values to do so. Now I think you can already see, especially in this image, that we are getting a similar result as was perceived at 3T, where the gray matter of the cerebellum shows this more intense diffusion signal compared to the gray matter of the cortex. And sort of at the, because we knew this already from the 3T scan, of course, we wanted to confirm this. And here you can see the relative diffusion signal in the gray matter of the cerebellum versus the gray matter of the segmentation in the cortex. And we really could see that the signal was very different. And this is just very different from what we see in a T1 image, of course. So it's a contrast, an extra addition as a contrast. But since we implemented this at 7T, we could also now finally look at different cerebellar areas. So we looked at this relative signal across the cerebellar lobules. And here's an example of that. So the top lobules that are darker and have lower relative diffusion signal, they are in the anterior lobe. And here at the bottom is the posterior lobe. And there we find higher relative diffusion signal. This is quite interesting, I believe, because when we look at histological studies, here is a study that looked at the granular layer thickness using histological data, but they reconstruct this onto a surface. They could see that in the anterior lobe, the granular layer is relatively thinner compared to the posterior lobe, and this is in healthy volunteers. So hopefully this is the beginning of an indication that this could be what we're capturing using this sequence. Maybe we are potentially somewhat capturing the granular layer here of the cerebellum. So I hope I've given an overview of all the different aspects, well, many different aspects of cerebellar imaging, also with respect to diseases such as multiple sclerosis, but also really the segmentations that come with it and the need for high resolution imaging when we're looking at the cerebellum. So I would like to thank you all for listening and let me know if you have any questions. Thank you.
Thanks so much. So we have 2 questions on the diffusion thing online. Before that, maybe I have a question on the fMRI. So in the cerebellum, is there something like a vein problem as well? Like you're maybe not for layer fMRI, but even kind of to separate these tiny lobules, is there a vein bias in gradient echo bolt that you need to worry about? And when does this start to come into a problem?
Yes, you do have to worry about it, definitely. It's mostly located. So there's sort of a draining vein. Let me see if I have the slide. At the back of the cerebellum. So here, so you can't really see it here. I think I need a posterior view here at the back. So here in this area is where you have the draining vein. And there you do see a lot of bias, and you sometimes see an entire cluster. The good thing is that this is relatively far from the motor activation. So usually they are distinct clusters. Sometimes you do see that this becomes a bias. So what you can do is make a vein image as well, location, and subtract this and use this information, of course. Definitely.
Maybe I have another acquisition question on so you talked about interference, like with B1 plus, and then your universal pulses help with that. How much of a problem, or like cerebellum is very challenging, and how much does these challenges coming from just kind of destructive interference, and how much is it kind of transmit coil geometry? Like there were these early, I think even fMRI studies with cerebellar coils and those kind of things.
Yes.
Is it just that the coil is too far up, or a combination?
I definitely think it's a combination. The cerebellar coil had much better results using the surface coil at the back of the cerebellum. The problem there is, of course, that then you're lacking your whole brain images in your registration purposes. But yeah, I do think it's a combination. But I also think the positioning of the coils relative to the brain and the cerebellum is very problematic because it's just not even reaching the coil sometimes. Yeah.
Yeah, great talk. I was really intrigued by the very end where you were talking about diffusion coefficient. And it just, so, you know, one of the big things that people are trying to get at, you know, at least in structural imaging is neuron density. You know, it's sort of a metric that, you know, some people are trying to get. And have you tried, I mean, it seems that, have people tried to look at, like, you know, knowing the neuron density approximate of cerebellum versus gray matter, whatever, trying to get some sort of proxy of, you know, just see how it correlates with diffusion coefficient? Because that would be, I mean, obviously there's many other variables, but it would just be interesting to see how it correlates with neuron density, how it correlates with it.
Yeah, I think definitely, I think also in Lund, there are different sort of studies looking at how you can use the models of the layers itself as a sort of indication of how the signal would behave with respect to this. So yes, that's definitely happening. And for the cerebellum, you would need of course, adjusted model based on this layer structure. But I definitely think that would be a very interesting next step. I think in this project, the main goal was just doing this implementation. Scanning the phantom was already, really the first step, and then doing it in vivo. But I think once it's a stable sequence that we can use across scanners, then I think it's definitely something we would look at. Yeah. Do I have to look at it? I can't see them here.
We have a question from Salim. I guess about the possibility to combine Maastricht and Lund. His phrasing is, have you obtained diffusion MRI data from the postmortem specimen to identify the projections to different cerebellar lobules?
Yes. Interestingly, yes. I was looking to, so Allard is the person, wait, I can show the data again, where they acquired this data, and yes, they do. So the first step was to do the segmentations, but they do have diffusion images. Not exactly sure on the specificities, I haven't received those, but we basically want the more contrast, the merrier, and I think that should be very interesting. Yeah.
Another online question on those data, the diffusion data is from Robin. Which algorithm to solve the inverse problem for cerebellar reconstruction was used for the super resolution?
Yes. So this is from the group of Marcus Nielsen. I have it's on GitHub. It's open source. It's available. It was a method optimized for Siemens, and then we adjusted it to work for Philips, but that was mostly a coordinate space difference. So yeah, it's really available. I can look up the link for it. Yeah.
One other quick question. I mean, I was really also intrigued by the totally different organizational structure, of the cerebellum in terms of like the outer rim versus the inner. You know, that's totally different. And right, it was clever how you used Lanny to look at that way. I mean, do you think there's any finer structure within? I mean, obviously there must be within the layers that's what's involved. I mean, what is that? I mean, what's the principle of that gradient again, of like outer to inner? Is there some sort of principle that helps?
I looked into this. Yeah, I found this really difficult also to figure out, especially because these studies were performed, I believe, in mice, and there they use electrophysiology, so they literally look at where is the signal. But in humans, it's hard to structurally, even when you look at it at this resolution, I don't know why you would have it more here compared to here, for instance, but given that also our indication shows this would be related to the posterior lobe and not the anterior lobe, there I'm also not entirely sure. But generally in cerebellar function studies also sort of the question whether it's the cerebellum as a connection to the cortex, or are these one-by-one relations, or are these not? And I think you have studies indicating either. So yeah, honestly, biologically, I'm not entirely sure. Yeah. Yes.
I was curious, and so you collected two different B values, but then the results that you were showing were only associated with the higher B value, the 3,500.
Yes.
Did you do any kind of linear fitting between the three B values? Does that add robustness to your measures, or?
Yes. Yes, we did. So everything, these segmentations that you see, this as well as this, I did for both B values, and you get exactly the same differences. You just have a signal. So the order of magnitude is different, but you get exactly the same pattern. We also did, well, as much as you can fit two B values. So we plotted both, and we can see a similar behavior across participants. But yeah, we were really limited by the gradients of the scanner, because the reason we have 3,500, the scanner was already suffering, I would say. It tried its best, but you're also reaching a noise floor very quickly. So we tried 4,000 and I believe 4,500. And then here we had, you do see noise here, but we still had enough signal to noise to see the comparison. But yes, so I did the analysis for both p-values. Yeah. And the B0 image is basically used to remove the bias towards any, I don't know, B1 homogeneities or any other homogeneities that we get from the zero image. Yeah.
And is it a really uncomfortable sequence for patients? I mean, the gradient switching on the spherical tensors is very fast.
Yeah, I would say it's highly uncomfortable, and it needs, yeah, people who've been in the scanner many times. And I think this is mainly because we're just reaching the limits of the gradient. So I would say it worked. We scanned 11 participants in the end. But I would say if we would want to continue with this, we would have to look at different gradient systems, probably. Because yeah, the switching and just generally the shaking, everything. So yeah, definitely. Yes.
Near the beginning, you were talking about sort of the personalized shim versus sort of a cerebral.
Yes.
You said the personalized shim took 7 minutes. I'm curious, is that sort of from like an unshim state, or did you try starting from the universal and sort of personalizing from universal shim?
No, this is the 7 minutes came from basically what we used before we had the universal shim, and this meant basically the acquisition of an anatomical locator, then the participant at the scanner quickly drawing an ROI, because you had to do that there, and then the calculations, of course, they're not that long. But that's an interesting idea. Yeah, you could indeed start from a the universal shim that we have and optimize it further. But what we see is that generally it actually works quite well. The differences aren't that big to use the universal shim. So there's, at the moment, I don't think really a need to have it optimized. But if we would have a lacking signal, then I think it would be useful. And possibly also it might be useful to sort of adapt it to at least a range of brain sizes or something like that, because we do see that when people have a very large brain, then you do still get homogeneities. Yeah.
Speaking of shimmy, do you think with smaller brain, and I'm thinking about kids, it would be possible to get a perfect shim both in the cerebellum and in the frontal cortex?
Well, I guess this would also depend on still the positioning of the head with respect to the coil. But I'm not sure. I mean, I've never, we've never scanned smaller head sizes, but I would imagine you get a lot more homogeneous signal. Yes, I think so. It would be less of a problem. Yes.
Thank you for your talk. The perspective motion correction you recently MP range, is that one of the camera-based systems or was it built-in navigators?
So this was an interleaved bat navigator during an MP2H sequence. So yes, it interleaves. Yeah.
And how long did the 0.1, the 100 micron, 200 micron whole brain postmortems?
The 200 micron, they did a T2 star fit. So there they wanted different echoes. So that took 2 times 5 hours. The whole brain 100 micron was at 1 echo time, and this was 22 hours. Yes, not something we want to do in vivo yet.
Maybe I have another question about one intriguing result of the bilateral responses that you get for extension, but not for flexion or anything. And you kind of disclaimed in saying that you don't really know where this comes from.
Yeah.
You mentioned complexity, like in the cortex. Not all the kind of corticospinal tracts kind of cross the hemispheres. Mm-hmm. So there also, when kind of you do very complicated tapping, it like this has been seen. Do you think it's complexity, or how are the cerebellar spinal connections going on? What is your hypothesis? That it's a completely different kind of way of
it is. Yeah, you sort of get back to this. Is it the cerebellum, or is it because the cortex is doing it and thereby the cerebellum is doing it? I think answering that question is just very difficult. I think I looked into, when I saw the results, it wasn't necessary, we didn't expect this, so it wasn't something that we had a hypothesis for in mind. But then I just started looking at papers on bilateral activation when doing a unilateral response, and then I reached complexity. So this was an assumption, but it's not, it could very well be the cerebellum itself. I think in order to properly disentangle this, we might need a more controlled task of looking at the cerebellum, because this, of course, yeah, the participants were doing it themselves. They reported that they found extending more difficult. So this is what we based that on. But of course, difficulty is also not that binary. So I wouldn't really know yet. But I thought it was interesting.
And kind of the topology or the topography of the fingers, does it match kind of on the other side? Is it because you had it with 3 fingers, right?
Yes, we looked into that. On the other side, we saw patches, but not necessarily a specific organization. Okay. So, but we did see different areas for specific digits, but we didn't see some topic gradients on this hemisphere. No. Yeah.
Are there any further questions? Oh yes, Salim has a suggestion. Maybe that's a follow-up with respect to merging the ex vivo and diffusion. Include the labels for the fMRI activated regions. It's a suggestion for slides, I guess. Brackets, all the different fissures between the lobules in your maps.
Okay.
He has another comment about the microstructure. Also, can you identify all the subregions of deep cerebellar nuclei in your maps? Okay, that's also, I guess, an addition to the suggestions for future slides. Maybe.
Yes, yes.
Are there any questions in the room? No. Then thanks a lot.
Thanks
a lot, and see you later.